Hi everyone. In this video, we will see an overview of methods for enhancing LLMs, approaches that will help us get the most out of a language model. This includes prompt engineering, RAG, and fine-tuning. Prompt engineering is a technique for crafting effective prompts that guide the LLM to provide desired output. So prompt engineering helps to get higher quality output and be more efficient with LLMs for achieving specific goals with fewer number of prompts. Let's start with an example. Assume we want to build a travel itinerary and we start with this naive prompt. Build a 4-day itinerary for a trip to Seattle and include activities for each day. This is not an effective prompt for the following reasons. The prompt doesn't specify who this itinerary is for. It doesn't specify the interest of the user, whether the user is into outdoor activities or museums, etc. And as a result, it may output a generic response that may not fit to the user's preferences. Therefore, the user may have to iterate a few times until they get their desired output, which is very inefficient. To make an effective prompt, we can consider these 4 key elements. First is clarity, so we have to clearly describe the task that we want the LLM to solve. Second element is the context, so we have to describe the background and provide all the necessary information for the LLM. And the third element is specificity, which means we have to provide the details to be able to get the precise answer. And finally, craft the prompt with instructions and using instructive verbs like explain, summarize, compare, or itemize. So taking these elements into account, here is the improved prompt for building a travel itinerary. In this prompt, we have determined the specific audience that this itinerary should be tailored to, so that is a family and including cat-friendly activities and also including vegetarian restaurants. Also, we have determined which types of activities the user wants, like outdoor spaces, like parks and waterfronts. There are a few strategies for crafting more advanced and effective prompts. The first strategy is to start the prompt by adopting a persona for the LLM. For example, we tell the LLM you are a medical expert or you are a financial consultant. In the next step, we describe the problem or the task that we want the LLM to solve. For example, we say that the user wants to learn German and they can allocate certain amount of time per week and so on. After defining the problem, then we provide the detailed instructions on what we want the LLM to do. Sometimes this is left behind and the LLM assumes this step, but it's better to explicitly describe the instructions. And finally, how we want the output to be. Do we want the output as just text or breaking it into sections, or even provide the table as output or just in JSON format? Now, here is the revised prompt that is built with these 4 strategies. First, we tell the LLM to adopt a persona as an experienced travel consultant with a very good knowledge of Seattle's attractions. Then we describe the task in details, including users' interest and preferences. And after that, the instructions for how to build the itinerary. And finally, describing the output format, in this case using headings for each day of the trip to make it easier to read. The knowledge of an LLM is acquired during training on massive amount of data. This knowledge is stored in the parameters of the neural network model and therefore it's often called the parametric knowledge of the LLM. After the LLM is fully trained, a typical workflow of LLM inference is that the user will send a prompt to the LLM and then the LLM will generate a response according to its parametric knowledge. However, the parametric knowledge of the LLM may not be sufficient for answering all prompts. The reason is that this knowledge is static and has a cutoff date based on the latest information that the LLM has been trained on. So if you ask a question about more recent events after the cutoff date, it will not be able to answer that question. In addition to the static knowledge of LLMs, there are a few other issues as well. LLMs are trained on broad datasets, but they lack in-depth knowledge of specialized domains such as medicine, law, etc. Furthermore, the parametric knowledge of LLMs is restricted to public data, So they cannot generate responses based on private or proprietary information like internal organization documents. And finally, if we try to feed a very large document to ask questions based on that document, we should note that LLMs have limited context window, so there is a chance of information loss when processing very large documents. Knowledge-intensive applications are systems where the goal is to retrieve relevant information from extensive and specialized data sources. But due to the reasons we mentioned previously, direct application of LLMs is not suitable for such knowledge-intensive use cases. Instead, a better solution for such systems is RAG, which combines the power of LLM for processing natural languages with information retrieval systems. So in this paradigm, on the right, as the user interacts with LLM, the retrieval system will pull the most relevant information from the database, and then the LLM will provide the response based on the retrieved information. A RAG system is built for a new data source, which is also called the external data because it is external to the LLM. First, this external data is split into chunks, and the embedding vectors for each chunk is computed and stored in a vector database. Then, when a user sends a prompt, the same embedding model is applied to the prompt, and an embedding vector is computed for that prompt. Next, we perform a similarity search between the prompt embedding vector and the vectors stored in the database. From this semantic similarity search, the most relevant chunk of data is retrieved from the database and is fed to the LLM along with the original prompt. So the LLM will provide an answer based on both the prompt from the user and the retrieved data from the database. Pre-trained LLMs are considered general-purpose language models because they have a vast general knowledge. However, they lack specializations in specific tasks. Fine-tuning is the process of updating the parameters of the LLM for adapting it to a specialized task. Let's see a motivating example to get a better understanding of LLM fine-tuning. A vanilla LLM is a model that has only been pre-trained for predicting the next word. So if you ask a question like, what is the distance of Mars from Earth? This vanilla LLM only knows how to predict the next word after this prompt. So it may come up with similar questions like how far is Jupiter from Earth instead of answering the question. That's because the vanilla LLM is not trained to follow instructions. An instruction-tuned model is a model that is fine-tuned to follow instructions. So if we ask the same question from the instruction-tuned LLM, it will provide a proper response instead of generating similar questions. There are two categories for fine-tuning LLMs: supervised fine-tuning and reinforcement learning with human feedback, or RLHF. In supervised fine-tuning, we have a clear set of input-output pairs that we can use to train the model. For example, for instruction tuning task, we have a set of prompts that are paired with the correct answers. SFT has several use cases, like for domain adaptation, building task-specific models, or even fine-tuning an LLM on low-resource languages to improve its performance. The second category, RLHF, is for more complex tasks where we don't have a clear target for the prompts, and instead it is trained based on human judgment. This is often used for aligning the LLM with human preferences, for example, to prevent harmful content, as well as ensuring that the LLM responses comply with company policies. So we have seen an overview of these three approaches. Now the golden question is which approach to choose for a given problem. Do we need prompt engineering, RAG, or should we fine-tune the LLM? So in such case, we can ask these questions to see which approach is best suited. If the problem does not need any new data and it can be solved simply by more effective prompting, then obviously prompt engineering is the approach to take. For knowledge-intensive applications where we need to generate responses based on some external data, we need to choose the RAG model. And finally, for other applications that we really need to update the parameters of the model to improve its performance, we can choose the fine-tuning approach. So that brings us to the end of this video. I hope that you enjoyed watching this video, and in the next video we will build a rack system from scratch. So thanks for watching.